Okay, so this is problem 2.21 out of Griffiths, and wants us to find the potential inside and outside a uniformly charged solid sphere whose radius is r and total charge is q. Use infinity as your reference point. You could calculate the gradient of v to check your answer, but the way that I'm doing this, it doesn't really make a lot of sense. So what I was actually going to do is find the E field first, and then from there find the potential. So I'm going to do the E field using Gauss's law. So for our Gaussian surface being smaller than the actual radius, I don't know, let's say it's something like that. Gauss's law tells us the closed surface integral of E dot dA is equal to Q enclosed over epsilon naught, which is the magnitude of E times 4 pi r squared. That's the dA, coming from the dA of our Gaussian surface. Q enclosed over epsilon naught. So we need to get Q enclosed. So Q enclosed, as we know, is rho d tau. This has charge per volume, and this is volume, so you get your units of charge. And one way you can think of rho is the charge, Q, divided by the volume of our whole sphere. And d tau, that's our volume element of our Gaussian surface. And when you do that, you can see you get Q little r cubed over big R cubed. Your 4/3 cancel, pi cancels, and you're left with that. So the magnitude of our E field times 4 pi r squared is equal to Q r cubed over r cubed epsilon naught. So then finally we can say the E field as a vector is equal to, well, we're actually going to be dividing over the r squared here, so that'll cancel with all but 1 here. So we'll be left with Q over r, 4 pi epsilon naught, big R cubed, r hat. So this is the electric field inside our Gaussian surface. So that's inside, just as an example, the green one I drew. But just as easily, we could have had something outside, and that's something we're going to need. And it's just as easy to find this. This also has, obviously those little r's are different, but I'm just using little r as our Gaussian surface. So we also want to find when r is greater than or equal to the radius of the actual sphere. So again, we'll do the same thing, which is Gauss's law. The left-hand side of our equation is not going to change. We have Q enclosed over epsilon naught. Now, Q enclosed is just Q for when we're outside the sphere. So that actually makes this really easy. All we have to do is divide over, and we'll have our E field. So our E field is Q over 4 pi epsilon naught r squared in the r hat direction. So now we have our E field in and our E field out. And with that, we can find the potential. So let's say we do delta V, and let's say we're going from out from infinity in towards R. Well, that's going to be equal to negative the integral E, we'll call it dl, from infinity to, we'll call it actually lowercase r. Where do they want the potential exactly? Inside and out. Okay, so let's do this. Let's start by finding the potential outside. So this is outside, right? So V sub r, and again, V at infinity is 0, that's our reference point, is negative the integral from infinity, this should be a capital R. And what we want is the E field outside. So what is the E field outside? Q over 4 pi epsilon naught r squared dr. Okay. So the potential outside your sphere, well, that's going to be, we can factor out all these constants. And then I use the exponents to go ahead and bring that guy on up. So if we do the power rule here, we can add 1. That'll make that a positive number. And then we just bring it down. So you'll end up with Q over 4 pi epsilon naught r. So that's the potential outside the sphere. So they want the potential inside and outside. So we just found outside. Inside, we want the potential now from, we'll say little r minus V infinity is equal to negative the integral from infinity to little r, E field dot dr, dl. And again, infinity is our reference point, which is 0. So VR, that's inside, is minus the integral from infinity to r of your E field outside, dr, minus the integral from big R to little r inside E field dr. So we broke this integral up into 2 different regions, and we actually have already done that one integral. That is going to be exactly the same as before. There's going to be nothing different. This is Q over 4 pi epsilon naught big R. But now we have to integrate from big R to little r, and your inside E field, which is Q little r over 4 pi epsilon naught big R cubed dr. Okay, so we can factor out a whole bunch of stuff here. So V at R is equal to Q over 4 pi epsilon naught R minus, I can factor out the Q, 4 pi epsilon. I can factor out a big R because we're integrating with respect to little r. And this one is not too bad to do. This is actually a very simple integral. So you'll end up getting Q over 4 pi epsilon naught big R minus Q over 4 pi epsilon naught big R cubed times 1/2. And then we can say R squared minus big R squared. Okay. You can factor out the 1/2. And you get 8 pi epsilon naught R cubed, R squared minus big R squared. You can try to factor out anything you might have in common. So let's see, every term has a Q and a 4 pi epsilon naught R. And you'll be left with 1 minus 1 over 2 R squared. So this is again your potential. You don't really need to do all this. I'm just factoring it, trying to make it look nice. You could distribute it if you wanted to. It's really not necessary to do all this work. I'm going to go ahead and just do one little bit because it does nicely cancel. So you'll end up getting a 1/2 here. I guess if you wanted to, you could add that 1/2 1/2 plus 1 is 3/2. You could factor out a 2. Q over 8 pi epsilon naught r. 3 minus little r squared over big R squared. It's about as simple as you can get it. So this is your potential at R. So this used a little bit of your E field. Now there was other parts of the question where they wanted you to confirm it by taking the gradient, but that's kind of redundant. We just took the E field and we integrated it. So obviously if we do the opposite of integration, we'll get the same answer. I guess that's a way to check to make sure your integration's correct, but I don't think that's really necessary. So hope